So good day everyone. Our topic is about the development of the probability theory of Pascal, Bernoulli, and Laplace. So I will discuss about Pascal. Who is Pascal? Blaise Pascal is a French mathematician who is popularly linked with Fermat as founders of the probability theory. So Pascal is also a creative mathematician and experimental physicist. Also a general reader as author of the greatest prose classic in the French language and etc. So he is also known for Pascal's mystic hexagon theorem. So a hexagon is a six-sided polygon. So if an hexagon is inscribed in a circle, the 3 points of intersection of the pairs of the opposite sides lie on a straight line. To spell it out in more detail, Pascal had this to say: inscribe any six polygon in a circle. So gawa daw kayo ng any six-sided polygon sa loob ng circle. So or more generally in a conic. And label the vertices to A, B, C, D, E, and F. Extend a pair of opposite sides. Let's say A, B, and D and E. So until they meet at the point P. And then extend another pair of the opposite side, say AF and CD, until they meet at a point Q. So nearly extend the third pair of the sides so that they meet at point R. So the mystic hexagon theorem states that P, Q, and R will always lie on a straight line. So to explain this more, this is an example or the represented graph. As you can see, we'll do it on the paint to explain it. Paint. So space it here. So as you can see, the first side is A and B, D, E. So let's color it as red. So if A and D, this is A and B, extend. This is A and B, which extend it to here. So this is point P. And then if E and D is also extended, and this is the time the point of P is created. So another is AF and CD. So let's try side A and F, or F to A. So FA, line F and A going to the endpoint of Q, and then D and C, or CD going to the endpoint of Q. So next we have also B, or line BC or CB. And then line FE or EF when extended. So according to Pascal, they all end up with the same point. So this point is what we call a tangent line that connects the three, the Q, P, and R. So I will give you another example. Let's make a new one. So assuming that we have this circle. So hexagon is a six-sided part. So we have this, let's color it red. Label it inside of a circle. So, after that, ang sabi niya, label them to A, B, C, D, E, and F. So, this time, we will choose what side do we want. So, let's move first the figure para mas malaki ang space natin. So, let's start. If we extend line FA or line AF like this, and then extend BC or CB, which its opposite side. So this is the opposite side. Next, we also have line BA or AB. We make it longer para alam natin na saan ang endpoint nila. And then another, his opposite side is EF or FE. It's not straight. Oopsie. Yan. Let's now erase the excess part. But before that, we need to draw the straight line that folds them. Yan. So next, let's erase the excess para mas klaro. So ayan. And then label them. So let's label them. This is P, point P, and this is point Q. So we already proved that Pascal's theorem, or the first theorem that he has, is true. So another figure or a theorem is just the same with the first figure. As you can see, the E and F is now at 1 point. So, yung kanina, si E, si F, nandito siya. So, ang kinonect nila ngayon, ang pagkakaiba nila, which is si E at saka si A, ang nagkaroon ng line. So, napunta dito si F sa E. So, si E, it has 1, 2, 3, 4 lines connected to this 1 point. So, it's still the same. They have the tangent line, has the same points. Q, P, and R. Ang pinagkaiba lang nila, kasi si Q, andito lang, hindi extended ang kanyang angle. Pero dito, si Q, extended ang kanyang angle, but they still have the same tangent line. So next, we have the Pascal and cyclode. From the word cyclode means it's a cycle, or basically it's a repetition. So for only one brief period towards the middle of 1658 did Pascal thoughts revert of mathematics. So this was in connection with a curve that was enjoying a considerable vogue in its own special world, the cycloid, or the curve traced out by a point on a circumference of a wheel. As a wheel rolls along a straight line, on account of its elegant properties and the endless quarrels that it has engendered among eminent mathematician who has pretended to its favor, the cycloid has been called the Helen of geometry. So, the cycloid has been called the Helen of geometry. The accompanying figure shows a point P on a cycloid determined by three different positions of a circle. So, point P ang tawag sa cycloid na nakikita sa position of a circle. So, sa figure na ito, makikita nyo. Sige, expand natin para makita. So, as you can see, sa point P, ito yung tinatawag na cycloid. Cycloid niya. Si point P. And then si point P. So, yung point na yan ang tinatawag na cycloid. So, which is kahit anong circle pen, kahit ilang circle pen ilagay nyo dyan, kung sa isang arc, ganito sa isang arc, may point sila of intersection, which is called the letter P, yun ay tinatawag na cycloid. Next, the Demir's problem of points. Demir's reasoning is a passage just cited seems to be this. A perfect die has a 6 faces. So, die meaning isang die lang, which is 1, 2, 3, 4, 5, and 6. So, mark with 1 to 6 dots. Any of these faces is equally likely to show up a single cast because nothing in the shape or die of method showing it favors of a particular face. Thus, the probability of the 6 will appear in a single throw is 1/6. This might be restated by saying the probability of not getting a 6 is 5/6. If the die is thrown twice, there are 6 times 6 probabilities or 6/6 probabilities outcomes, and 5 and 5 of them do not produce a 6 either time. So, of the probability of not getting 6 in 2 throws. So, 2 throw is 5/6 to the power of 2. Continuing the argument, it can be concluded that n throws, the probability of not getting the 6 is 5/6 n. Hence, the opposite situation, having a 6 turn up at least once, occurs with the probability. So here, ang sabi nga kanina is 5/6 raised to n. So itong n, ito yung probability of throws niya kung ilan pwede ang niya, yung ilang beses ito throw ang isang die. So to have a better chance, so ang solution niya is 1 minus 5/6 raised to the power of n. Then ang sagot dito must be greater than 1/2 or 0.5. So, if it turns out that n is equals to 4 or 4 times i-throw yung die, so 1 minus 5/6 raised to the power of 4 is equals to 1 minus 625 over 1,296 is equals to the same, 671 over 1,296. Kapag i-convert din natin to as decimal point, 671 over 1,296. So it is 0.51, which is greater than 1/2. So 1/2 is 0.5. Or kapag i-round off pa to, pwede siya maging 0.52. So, which is greater than 1/2. Yun na nga. Thus, the demerit could be probability bet on throwing a 6 at least once in a 4 throws with a single die. When throws with a 2 dice are considered, the computation become more laborious. So suppose we paint one die red and the other is green so that we can tell them apart. Let A and B denote the event in which red die show in A and the green die shows in B. Then all possible outcomes for a throw of this colored die can be exhibited by 6 by 6 array. So, ito ang pinaka-highlight kay Pascal. So, he is very known to this. So, the Pascal arithmetic triangle. So, the Pascal arithmetic triangle is now generally known as Pascal's triangle. So, tinatawag na siya ngayon na Pascal's triangle. So, it is an infinite numerical table in a triangular form where the nth row of the triangle lists on the successive coefficients of a binomial expansion of x plus y to n. Kasi 'di ba ang binomial expression natin is x plus y to the power of n. So dito sa Pascal, it's the same, related siya, pero ito kasi sa kanya in a triangular form. So for example dito sa ano niya, so ito, si 1. Si 1, oh. 1 talaga yan, always. And lahat yan dito sa side, sa dulo, always may 1. We always add it to 1. Same din yan siya dito. So when we add 1 plus 1 is equals to 2. So next is 1 plus 2. Dito sa gitna nila, every middle of each number will be add. So 1 plus 2 is 3. So automatic yan, maglagay ka ng 1 sa before the number and after the last number niya. So 2 plus 1 is also 3. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So add again 1. Add also 1. So 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And so on na yan siya. So, ito ang row 0. Ito ang first row, second row, third row, and then the fourth row, and the fifth row, and so on na yan. Kung ilan row ang ipapahanap sa inyo or ang gusto nyong hanapin. So, let's erase. So, next. So, ito. Another is, tinatawag to siya, kay Pascal din to, pero hindi niya lang pa na-arrange to. Ito yung top-down na arithmetic triangle niya. So, paano nga ba to? Di ba medyo magulo siya kasi ang daming lines kung paano ba to siya kukunin. So, it's like this. Ito natin para mas klaro. So, first, we have the parallel lengths or yung pag ganun. Going here like that. Ganon. So, we have, it's the same dun sa Pascal, di ba? Dito sa taas, may 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dito rin si, 1, 2, 3, 4, 5, 6, 7, 8, 10. So, this is the row. Ang row nila, tawag nila. So, ito, automatic yan. May 1 na naman dito. So, when we add, ganito yan ang add niya. Dito yan sa gitna. 1 plus 1 is equals 2. 2 plus 1 is equals to 3. 3 plus 1 is equals to 4. 4 plus 1. Sino? So 1 plus, again, let's resume. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. 6 plus 1 is 7. And 7 plus 1 is 8. 8 plus 1 is 9. So ito under automatic, may 1 din sa dulo niya. So next row, for the third row, we have 1. Ito din. Always yan. Dito yan sa middle nila ang sign ng addition. Lahat yan sila until the end. So we have the third row. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. And then 10 plus 5 is 15. 15 plus 6 is 21. 21 plus 7 is 8. 28. 28 plus 8 is 36. And so on. So, ganito na yan siya. Hanggang dito na yan siya. Continuous yan siya ganyan. So, di ba alam naman natin na ang triangle, hindi yan siya sabihin na they have the same, nag-end yan sila dito, lahat ganyan. Kasi magiging square na siya, hindi na siya magiging triangle. So, kaya, ang kanilang mga endpoint, lahat may minus 1 or something ganito. So, dito. Bakit eraser pa rin hawak ko? Wait. Bakit ayaw mo mag-draw? So, ayan na. So, sorry kasi bago pa lang ako magamit. So, as you can see, triangle yung form na kailangan natin. Ganyan. Hindi siya pwede mag-extend. Hindi siya pwede magdagdag dito. Hindi rin siya pwede magdagdag pa ng 2 dito. 3 dito. Continue na kasi ang mangyayari. What will happen kapag dinagdagan siya? Magiging square na. 'Di ba? Pag puno siya lahat. So, hindi na siya tinatawag na triangle. So, let's continue. Now, we're done with the parallel ranks or yung ganyan. Next, perpendicular na naman tayo pag ganun. Pataas or pababa, ganyan. Column down. So, it's the same sa ginawa dito. 1, 2, 3, 4, 5. On the first row or the first row, lahat yan 1 talaga. So when we add, it's still the same. Andito pa rin si addition sa kanilang gitna. Hindi klaro. Let's change it. Okay. So dito yan siya sa gitna. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. Wait lang. Dito na yun sila sa gitna pala. I'll make it clear. So, dito yun siya sa gitna. 1 plus 1 is 2. And then, 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. And then 1 plus 5 is 6. Bale, ang kwan niya is magkatabi, 1 plus 6, and then pababa nilalagay yung answer. So, ganyan. So, 1 plus 6 is 7. 1 plus 8 is 9. So, next we have 1 plus 1. Dito pala, Wait. Clear, erase. So, si 1 plus, saan ako? 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. Mali pala. Pag ganyan pala pa rin. Pag ganun. Going here o yung solution niya. Sana yun. No. Let's make it blue. So pag ganun pa rin siya. 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, then nandito sa baba. Yung kanina, 1 plus 1, 2, 1 plus 2, 3, 1 plus 4, 4. So, ganyan. So, next, ito na si 3. 1 plus 2, 3. 3 plus 3, 6. So, 4 plus 6. Ganito yan siya. Dito. Dito siya. Si 3 plus 3. 4 plus 6. Si 5 plus 10. Dito siya. Pababa na, di ba? 6 plus 15. And then 7 plus 21. 8 plus 28. So, ganyan. So, ito yung mga answers niya. Next row, we have 4 plus 6. Yan. Sila, 4 plus 6 is 10. 4 plus 6 is 10. 10 plus 10 is 20. 15 plus 20 is 35. Ito. And then 15 plus 35 is 56. And so on na yan dito. Okay, so next, let's move on to the next round. If you have questions, you can ask later. So ito kay Euler's. Ito na ba yung next? Okay. Hindi siya kay Euler, pero si Euler kasi nag-design siya ng binomial coefficient which is n over r. So, si Pascal, he decided that gawin siyang permutation. So, dito papasok yung permutation natin. So, yung sa kanya, symbol ng n and r pa rin. They are still the same. Yung sa kung yung n and r kay binomial coefficient siya, addition lang yun. Same lang man sila din addition. Pero dito kasi permutation, when you talks about permutation, meaning ito yung multiplication na siya. So, it's stated in the symbols that the property of the numbers is n and r on which arithmetic triangle is based n over n r minus 1 plus n over r is equals to n plus 1 and r. So this rule of course does not give a formula for the binomial coefficients. So hindi yan siya formula ng binomial coefficient, but it tells us how to build them or form two numbers in the previous base. So ito, in independent. So, according kay Pascal, ito yung formula for n and r. So, n and r is equals to n and then n minus 1 times n minus 2 and so on until n minus r plus 1. So, si n, ito yung number na i-multiply. Si r is yung kung ilang repetitions yan siya. Kung ilan. Kung hanggang saan i-end yung permutation natin. So, divided by 1 times 2 times 3 or and so on hanggang saan nga ang limit ni R. So, if 1 is less than or equal to R, but R is also less than or equal to N. If we use the spacing notation n factorial, so ganito yan siya, 1 must be not less than or equal to r and so as n minus 1. So foregoing formula can be expressed more as simply as n factorial. So from this, from this one, wala na yung annotation. So from this formula, ito siya. So si Pascal, ginawa niyang simple. Ito ang formula ng permutation. Pero usually ngayon, ang permutation, nakakompute na siya sa calculator. Yes. So, scientific calculator. So, of a specific interest, as simple as, for example, if 0 factorial. So, let's change R as 0. So, lahat yan, then it's still N. So, ganyan lang. I-ano mo lang siya, substitute mo lang kung saan siya nakalagay. Di ba ang R, ito si R, ito si R. So, dito na ngayon si 0. Dito si 0. So, kapag i-compute mo yan siya, ganyan pa rin yan. So, ang sabi niya dito, R is equals to 0 and also, meron pang isa if R is equals to N. So, pareho pa rin kasi N man din siya. So, naging N sila lahat. So, ganun lang yan. Kapag maglagay din tayo ng number dyan, let's say, for example, like this. Paano ba? Clear ko muna to. Magbigay tayo if n is equals to 3. So, ganyan over. So, si R natin must not be greater than, sabihin na natin, 2. Factorial over 2 factorial times 3 minus 2 factorial. So, ganito na yan siya. 2 factorial and then 3 minus 2 factorial. So, pag i-manual natin yan siya, ito siya maging 3 times 2 times 1. Ito rin siya. Si 2 is 2 times 1. Ito naman si 3. 3 minus 1 magiging 1. So, 1 factorial is 1 pa rin. So, 3 times 2 times 1 is equals to 6. So, ito siya. 2 times 1 is equals to 1. Pwede let's say, pag andito rin yung 2. alisin natin tong, wait, lumipat. So, alisin natin si factorial dito. So, ganyan. 3 times 2 times 1. So, understood na yan. Maka-cancel natin to siya. Kasi 2 factorial din to. Then, itong si 1 factorial, magiging 1 lang man siya. So, 3 over 1 is equals to 3. So, if our n is equals to 3 and r is equals to 2, therefore, our factorial will be 3. Ganun lang yun. So, next. Let's go to the next. Wait. So, ito. So, according to Pascal, he created 19 properties or consequences that he called them as binomial coefficient. So, related pa rin doon at saka sa na-discover niya sa arithmetic triangle na ginawa niya. So, ito yung first consequence 2. So, these are some of the consequences lang. So, based on the given module, so n minus 1, r minus 1. So, as you can see, n is the number of r is still this remain minus 1 minus 1 minus 1. Dito naman yung n it deduct with the additional na kasi increasing na. Dito sa baba, remain lang minus 1. Dito is minus 1, minus 2, minus 3, and so on kung ilan ang number na given sa kanila. So, ang another consequence niya na nakita niya is also n over n minus r. So, pag ilagay mo yun siya, magbigay ka ng data or magbigay ka ng value ni n at saka ni r, automatic dyan na same din siya sa arithmetic triangle na lalabas kung anong row siya, kung anong row ang hinahanap mo. So, and also this one, 2 raised to n, or the very common. So, as you can see, kung ilan ang power, or ilan beses natin erase yung 2, let's say, for example, to 2. So, hanggang dito lang yan siya. So, 0 is to 1, plus 0 is, 2 is to 1, and 2 is to 2. Ganun. 2 times 0 is 0, plus, plus 0, 2 times 1 is 1. So, maging 1. So, plus 2 times 2 is equals to 4. So, ganyan yan siya. And that would be all. So, thank you for listening. So, the next topic would be Miss Angel Laika Macario. She will be the one who will discuss about Bernoulli. So, thank you for listening.
So, let's move on mathematical induction. So, mathematical induction is a mathematical proof technique. To recapitulate, the proof of a proposition P times N by the mathematical induction consists in showing that the statement P times N sub 0 is true for some particular integer N sub 0. And the assumed truth of P times K implies the truth of P times the product of K plus 1. We can then conclude that the proposition P times N is true for all N greater and equal to N sub 0. The proof of condition 1 is usually called the basis for the induction, and the proof of condition 2 is called the induction step. The assumptions made in carrying out the induction step are known as the induction hypothesis. Induction has been likened to an infinite row of dominoes, all standing on edge and arranged in such a way that when one falls, it knocks down the next in line. if either no domino is pushed over, if there is no basis for the induction, or the spacing between them is too large. The induction step fails. Then the complete line will not fall. Desmarais inquired into the number of rolls necessary to ensure a better than even chance of getting a double six. He thought that the smallest advantageous number of tosses should be 24, but patient observation had shown him that 25 throws were required. The answer 24 is gotten by an ancient but mistaken gambling rule that runs as follows. Consider a situation in which there is one chance in n of winning on a single trial, and let n be the number of trials required to have a better than even chance of success. Desmarais' rule is that n over n is a constant. In the case in which one attempts to make a 6 with a single die, n equals 6 and equals 4, so that n over n is equals to 2/3. Hence, if n is equals to 36, as for the two dice in tosses, aiming at a double six, n must be 24. Pascal had little difficulty in disposing of Desmarais' great scandal. In the case of two dice, there are 36 possible throws, and 35 of these do not give a double six. Hence, the probability of not getting two sixes is 35 over 36. If the dice are cast n times, then the probability of no throw of double six is 35 over 36 to the power of n. This means that the opposite event, getting double sixes at least once, occurs with probability 1 minus the product of 35 over 36 raised to the power of n. When n is equals to 24 and 25, it is found that 1 minus the product of 35 over 36 raised to the power of 24 is equals to 0.4914. And 1 minus the product of 35 over 36 raised to the power of 25, the answer will give 0.5055. Therefore, 25 is the smallest number of rolls of two dice that offers a probability greater than one half of achieving a double six. We shall show that p times 1 is true, and show how from p times k we can prove p times the product of k plus 1. The verification of p times 1 presents no difficulty, since it says that 1 cube is equals to 1 equals 1 raised to the power of 2 times 2 raised to the power of 2 over 4. We now go to the so-called induction step. Suppose that p times k is true, so that for this value of k, 1 cube plus 2 cube plus 3 cube plus so on plus k cube is equals to k squared plus the product of k plus 1 raised to the power of 2 and then over 4. To confirm that p times the product of k plus 1 holds, we simply add the term k plus 1 raised to the power of 3 to both sides of the last equation to obtain which is just the statement of p times the product of k plus 1. We notice that in this calculation, we merely assumed p times k to be true to show that it would guarantee the truth of P times the product of K plus 1. We did not concern ourselves with the actual validity of P times K, but only with the fact that P times the product of K plus 1 is a consequence of the assumed truth of P times K. Having thus verified conditions 1 and 2, we see that P times N must hold for all positive integers according to the principle of mathematical induction. In a typical illustration of mathematical induction, let us verify the assertion that the sum of the cubes of the n positive integers is equal to the square of the nth triangle number. The appropriate statement P times n in this case is 1 cube plus 2 cube plus 3 cube plus and so on plus n n raised to the power of 3 is equals to the product of n times the product of n plus 1 over 2 and raised to the power of 2 equals n squared times the product of n plus 1 raised to the power of 2 over 4. Now let us move on Francesco Maurolico's use of induction. Maurolico is one of the great geometers of his time. Also occupied himself with a geometric analysis of lenses, spherical mirrors, and the human eye. The chief record of his optical research, Potismi de Lumine et Umbra 1611, anticipated many of the findings in Kepler's own Astronomiae Pars Optica of 1604. Although Kepler seems to have been unaware of his predecessor's work, Maurolico came remarkably close to the correct explanation of the origin of the rainbow. The greatest number of Maurolico's mathematical writings are gathered together in his Opuscula Mathematica and Arithmeticorum Libri Duo, which were published as companion pieces of at Venice in 1575. In the Pythagorean tradition, the Arithmeticorum contains a variety of the properties of integers noted by Nicomachus in the Introductio Arithmeticae, to which Maurolico added his own simple and ingenious proofs. For example, his proposition 11 shows that the n triangular number plus the preceding triangular number is equal to the n square number. Expressed in modern notation, this is t sub n plus t sub n minus 1 is equals to s sub n, where t sub n is presented by the formula. The formula is t sub n is equals to 1 plus 2 plus 3 plus and so on plus n is equals to n times the product of n plus 1 over 2. Maurolico's simple proof is this. By the rule of formation of triangular numbers, t sub n is equals to t sub n minus 1 plus n. Adding t sub n minus 1 to both sides of this equation gives t sub n plus t sub n minus 1 equals 2t sub n minus 1 plus n is equals to the product of n minus 1 times n plus n equals to n squared equals s sub n. The rest result in Maurolicus arithmeticorium that is actually proved by mathematical induction is the proposition that the sum of the rest n-th integers is equal to the n square number. In present day symbols, this is 1 plus 3 plus 5 plus 7 plus and so on, plus the product of 2n minus 1 is equals to n squared. Let us put the proof in the format that we have used earlier. Here, 1 plus 3 plus 5 plus 7 plus and so on plus the product of 2n minus 1 equals to n squared. Here is the statement p times n. First, observe that p times 1 is true. Since 1 is equals to 1 squared, now to obtain p times the product of k plus 1 from p times k, assume that 1 plus 3 plus 5 plus 7 plus and so on plus the product of 2k minus 1 is equals to k squared. Adding the next odd integer 2k plus 1 to both sides gives 1 plus 3 plus 5 plus 7 plus and so on plus the product of 2k minus 1 plus 2k plus 1 equals k squared plus the product of 2k plus 1 is equals to k plus 1 squared. Therefore, the assumed truth of p times k implies the truth of p times the product of k plus 1. It follows that p times n is true for all positive integers n. Pascal was, as far as we know, the next person to use mathematical induction, and he did this repeatedly in the triangle arithmetic in connection with the arithmetic triangle and its applications contained in the proof of Pascal's consequence 12 of the triangle arithmetic. The result that we would write as the quantity of n of r over the quantity of n of r plus 1 equals r plus 1 over n minus r. The first one, which is self-evident, is that this proposition occurs in the second base because it is apparent that null is to standard deviation as 1 is to 1, that is, for n equals 1. The quantity 1 of 0 over the quantity 1 of 1 is equals to 0 plus 1 over 1 minus 0. As indicated in the statement of the lemma, we assume that the ratio is question holds in the kth case. That is, for all permissible values of r times the product of r is equals to 0, 1, 2, and so on, k minus 1, suppose the quantity k of r over the quantity k of r plus 1 is equals to r plus 1 over k minus r. On the basis of this assumption, it is to be proved that the quantity k plus 1 of r over the quantity k plus 1 of r plus 1 is equals r plus 1 over the quantity k plus 1 minus r. We start by using the rule for formation of the numbers in the arithmetic triangle, or namely that each entry is the sum of two numbers in the preceding base. To write, the quantity k plus 1 of r over the quantity k plus 1 of r plus 1 is equals the quantity k of r plus the quantity k of r plus minus 1 over the quantity k of r plus 1 plus the quantity k of r is equals 1 plus the product of the quantity k of r minus 1 over the quantity k of r, and then over the product of the quantity k of r plus 1 over the quantity k of r, and then plus 1. If the induction hypothesis is now applied to the quotients of binomial coefficients that appeared on the right-hand side of this equation, it follows that the quantity k of r minus 1 over the quantity k of r is equals r over k minus the quantity r minus 1, and the quantity k of r plus 1 over the quantity k of r is equals k minus r over r plus 1. From this, we arrived at the quantity k plus 1 of r over the quantity k plus 1 of r plus 1 is equals 1 plus the product of r over the quantity k plus 1 minus r over the product of the quantity k minus r over the quantity r plus 1 and plus 1 is equals to the quantity k plus 1 over the quantity k plus 1 minus r over the quantity k plus 1 over the quantity r plus 1 is equals to r plus 1 over k plus 1 minus r, which completes the indication step. Thus, the validity of the desired ratio for a certain value of n, namely n equals k, implies its validity for k plus 1. This is just what Pascal's second lemma asserts. So let us move on. The Bernoullis brothers, James and John. James is known for his numerous contributions to calculus, and along with his brother Johann, or known as Jean or John, was the founders of the calculus of variations. He also discovered the fundamental mathematical constant E. The ars conjectandi comes in 4 parts. The first is the reproduction of Eugen's De Ratiociniis in Ludo Allier, accompanied by a commentary on all but one of Eugen's propositions. Bernoulli's commentary, which often offers alternative proofs of the fundamental propositions and in some cases extend them, is of more value than the original tract of Eugen's. The second part of the ars conjectandi contains practically all the standard results on permutations and combinations in the form in which they are still expressed. Bernoulli said that others had treated these topics before him, especially Van Schuten, Lennes, and Waylis, and so intimated that his subject matter was not entirely new. In this part, he gave an array. Bernoulli's theorem, or which the French mathematician Poisson later called the law of large numbers, is accurately stated as follows. If P is the probability of an event, if K is the actual number of times the event occurs in n trials, if Z is greater than 0, is an arbitrarily small number, and if P is the probability that the equality Jk equals n, Pj greater than Z is satisfied, then p increases to 1 as n grows without bound. Of course, it may happen that for some n, no matter how large the difference jk equals n, ej will be greater than z in a particular sequence of n trials. What Bernoulli's theorem asserts is that those sequences in which the inequality jk equals n, ej is less than z is satisfied are much more likely to occur. With Bernoulli's theorem, the ars conjectandi ended abruptly. It is especially to be regretted that the promised application to matters of economics and politics remain unfinished because Bernoulli's theorem was to become the stepping stone from insignificant problems with burns containing colored balls or dice tossing and card playing to valuable and scientifically justified applications of probability theory or such as mathematical statistics, demography, and the theory of random errors. John Bernoulli, like his older brother James, ran counter to his father's plan regarding his work of life. Originally scheduled to take charge of the family's thriving trading interests, he escaped an unsuccessful apprenticeship as a salesman by getting permission to study medicine. The custom of issuing challenge problems to rival scholars was resumed by the early practitioners of the calculus. One such problem proposed by Leibniz in 1687, that is, a curve along which a body affected only by gravity will fall with constant velocity. In the Acta Eruditorum of 1690, James Bernoulli published his solution to the problem of constant descent. Solutions had already been given by Huygens in 1687 and Leibniz in 1689. The problem led him to the differential equation dy square root of b squared y minus a squared equals dx the square root of a cubed, from which Bernoulli concluded the quality of integrals of the two sides. In solving the equation, the word integral was used for the first time in its present mathematical sense. The required curve turns out to be semi-cubical parabola, or in simplest form, y cubed is equals to y squared. Let's move on the Moivre's doctrine of chances. Returning the development of probability theory, we tend that the next big milestone was the publication of the Moivre's doctrine of chances, or a method of calculating the probability of events in play during 1718. So this was the first English treatise on the subject. Abraham de Moivre was a French Protestant who was forced to seek asylum in London after the revocation of the Edict of Nantes and the expulsion of the Huguenots. There he took up his lifelong approbable occupation as a private tutor in mathematics. He had hoped to obtain a university professorship, but he never succeeded in this, partly because of his non-British origin. Because factorials increase with extreme rapidity, it is desirable to have an approximate expression for n that is convenient to manipulate both practically and theoretically. In the first edition of the Doctrine of Chances, de Moivre obtained a result, or namely for a very large n, it is known that n imaginary is congruent to Cn raised to the power of n plus 1 half and e raised to the power of negative n, which is complete except for the determination of an unknown constant factor c. In the second edition of 1738, he gave the formula with due credit to Stirling. Hence, the celebrated approximation, which is usually known as Stirling's formula, is at least as much the work of de Moivre. The next presenter will tackle about the mathematics of celestial phenomena, Laplace.
Hi, my name is Noreen Arlaksamana from BS Math 3A. I'm now discussing about the mathematics of celestial phenomena, Laplace. So, the full name of Laplace is Pierre-Simon Laplace. He was born on year 1749 and died on 1827. So, between the age of 7 and 16, the young Laplace was educated in a school attached on Benedictine Priory in Beaumont. He entered the University of Caen at 16, intending to study the theology, but soon he decided that his true colors lay in mathematics. So he wrote his first mathematical paper and was named a provisional professor. When he decided to go to Paris, he was total recommendation to Jean d'Albert. Then he was leading mathematician in France. The letters remain unnoticed, but Laplace caught the Alembert eye by addressing a long paper to him on the general principles of mechanics. So this brought the enthusiastic reply, "You need no introduction, you need recommendation yourself. My support is your due." So Laplace's genius was also shown in his contribution to probability and to the emerging theory of mathematical statistics. From 1774, he published a series of memoirs that he eventually expanded into a mature work, the 464-page Theorie analytique des probabilités, on year 1812. So the result of the greatest novelty here was his derivation on the so-called least squares rules of minimizing the uncertainty in the number of independent observations. The general formula embodied in this statement, PR times event, is equal to the number of the favorable outcomes divided to the total number of outcomes. In the Ars Conjectanti, Bernoulli wrote, "All cases are equally possible." So, proceeding to the basic results of probability theory, Laplace derived, among other things, the widely used addition and multiplication theorems of probabilities. The modern formulation of these follows. 1 is if A and B are mutually exclusive events, that is, they cannot both occur at the same time. So, the formula must be PR times A or B, D PR times A, C PR times B. The second is if A or B are two independent events, that is, the occurrence of one doesn't affect the probability of the other. So, the formula must be PR times A and B, D PR times A, PR times B. So the difference of the first and the second formula is, the first formula is you must multiply the PR in either in A or B, While the second formula, you must multiply both A and B. So this is the modern formulation. So for instance, if a card is drawn at a random from a standard breeds deck and a second card drawn from a Pinocchio deck, we might ask about the probability that both are aces. So examples, a breeds deck contains 52 cards, of which 4 are aces, and a Pinocchio deck of 48 cards has 8 aces. So denoting the events of getting an ace from a bridge and Pinocchio deck by A and B respectively. So we have this formula: PR times A and B is equal to PR times A, PR times B. So based on the given problem, we have the 4 aces is to 52 cards, which is, as you can see in the problem that we solved, is we have 4 is over 52 multiplied by 8 over 48, that get on the 4 aces is to 48 cards. So by the multiplication methods, we have 1 over 78. So if the probability of the success on a single trial is denoted by P and the probability of failure by D, Q1, P, then P and Q remain constant from the trial to trial. So Bernoulli showed that the probability of observing exactly R successes is N such trial was expressed by the R terms of the expansion for P plus Q raised to N, that is, so PR times R successes and NR failures is equals to N of R times P raised to R Q raised to N minus R. So the instant SS, SFF, F are R successes in the R trials followed by NR failures in the remaining trials. So because of the trials are independent, the probability of this particular event is the product of the P raised to R for the R successes and N Q raised to R minus N minus R for the NR failures. So the formula must be PR times SSF, F is equals to P raised to R Q raised to N minus R. So the total number of the ways in which the N trials can be divided into exactly R successes and N R failures equals to N of R. So because of these individual ways or mutually exclusive events, each having the probability P raised to R Q raised to N minus R, so the sum of these probabilities is N of R Q raised to N minus R. So let's say we have this example. So if 6 well-balanced dice are thrown, we might ask what is the probability that exactly 2 of the dice have 2 faces showing at least a V. So this can be viewed as Bernoulli trials experiment, in which the probability of P of the success is 1/3, a V or a 6 showing and failure Q is equals to 1 minus P is equals to 2/3. So the desired probability is therefore PR times 2 successes and 4 failures is equals to 6 of 2 times 1 of 3 square, 2 of 3 raised to 4. So is equals to 15 times 1 over 9 times 16 over 81. So 6 of 2 is equals to 15, and 1 of 3, when we multiply it by the square root of 2, 1 square is 1, 3 square is 9, so we have the 1, 9, and 16 over 81 is 2, raised to 4 is 16, and 3 raised to 4 is 81, so we have the 16 over 81. So by the multiplication method, we have 15 times 1 over 9 is 15 over 9 times 16 over 81. So we have the 240 over 729. So what is the probability that a person will win the prize in his probability of hitting on any given shots is? So if it was simply a matter of ending the probability of 3 and only 3 successes is 4 trials, Bernoulli formula would tell us that this occurs with probability PR times 3 successes on 1 failure. So we have the 4 of 3 times 3 of 4's cube times 1 of 4. So the prize will be won only in the 3 mutually exclusive cases, SSSF, FSSS, and SSSS. Hence, the probability sought in PR times SSSF plus PR times FSSS plus PR times SSSS. So, based on the given problem that we solved, so we have the 3 of 4 cubed times 1 of 4. We have 1 of 4 times 3 of 4 cubed plus 3 of 4 raised to 4. So we have the 135 over 256. So using the integral calculus, one can show the formula PD 2L times 3A gives the probability of P that the needle will fall across a line. Laplace was the first to point out by throwing the needle many times and assuming the statistical estimate for P, one can use this formula to arrive at an approximate value of 3. Sometime between 1849 and 1853, Johann Wolf, professor of astronomy at Bern, performed the actual experiment. In his demonstration, the width between the parallels was taken to be the 45 mm and the needle used was 36 mm long. So the needle was tossed 5,000 times and it cut line 2,532 times. Hence, the relative frequency was 2,532 divided by the 5,000. So it equals to 0.5064. So taking this value for the theoretical probability of intersection and setting, 72 over 45 pi is equals to 0.5064. So produce pi is equals to 3.1596, which differs from the known value of 3 by less than 0.02. The best result for this kind was obtained in 1901 by Lazare Raini, who was carrying out only 3,408 trials, found pi correct the 6 decimal places. So Laplace was led to extend Wolfram's problem to a grid of two mutually perpendicular sets of equidistant parallel lines. If the distance between members of the sets are A and B, the probability that needle of length L less than the A and B will intersect one of the lines. So P is equals to 2L times A plus B times L squared. So divided by the pi times A and B. So demographers proposed to reach estimates of the population of determining a factor by which the average annual number of births should be multiplied to give the approximate total population, which data from the sample census. Laplace calculated the ratio of the population M in the sample districts to the annual numbers and births in these districts. So he therefore estimated the whole population of France from the formula. Using this formula is P times is equals to M of N times N, where N is the annual number of the births of the nation as a whole. His sample taken from the 30 districts scattered over France produced the years 2037 2,037,615 inhabitants, and 4n is the annual number of births from the nation as a whole. So his sample was taken from the 30 districts scattered over France. Produce the years 2,037,615 inhabitants, and where n is the annual number of the births for the nation as a whole. So he's assuming the number of the births in France in the year to be 1 million. He concluded that the whole population contained people, and the amount of P is equals to 3 times 2,037,615 divided by the 215,599. So multiply by the 10 raised to 6 is equals to the 28,352,845. Perhaps the more significant problem was his estimation of the degree of error in these years. The first, estimate of error inherent in sampling, and a computation of how large a sample would be needed to reduce the range of the probable error to the specified limits. So the concept of mathematical expectation of one of the most important notions of the probability theory was introduced by Huygens as the value of the chance. So we probably owe the modern terminology to Van Scoten, because the word expectatio appears the first time in the translation of Huygens' tract for a long while space. Hope ran it close second choice to give as precise denotation if the possible outcomes of a game or experiment are given numerical values a sub 1, a sub 2, to a sub n. And these outcomes occurs with the probabilities p sub 1, p sub 2, and p sub n. Then the mathematical expectation E of the game is A is equals to a sub 1 times a sub 2, and a sub p sub 2, a sub n, and p sub n plus a sub n and p sub n. And examples will illustrate this idea. Suppose a gambler rolls a fair die, after which the casino pays his as many dollars as there are dots showing on the upper face. So we may denote the individual outcomes by 1, 2, 3, and 4, and 6. The possible number of dots showing each occurring with the probability of 1/6. Thus, the gambler's expectation per game is E is equals to 1 times 1 over 6 plus 2 times 1 over 6, 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. Since the fractions are the same, we have the 1/6 plus 1 plus 2 plus 3 plus 4 plus 6. So we have the 21 over 6 because of the multiplication methods. So by 21 over 6 is equals to 7 over 2. So this sum might be taken as a fair price to pay the privilege of playing the game. In a long sequence of games, a gambler paying this price would have an average winning per game near 0. For another illustration of mathematical expectation, consider the game of roulette. The wheel was 37 equally spaced slots, which are numbered from 0 to 36 inclusive. If a man playing roulette bets saying $1 on the given number, and if a ball comes to the rest in the slot bearing that number, we receive $36 from the croupier. That is, he recovers his bet and receives in addition 35 times the amount wagered. The player wins $35 with a probability of 1 over 37 since all the slots are the same size, and loses $1 with a probability of 36 over 37. So that his expectation is E is equals to 35 times 1 over 37 plus times negative 1 plus times 1 over 37. So by simplifying the given problem, so we have the 0.027. Since we have the 35 times 1 over 37, we have 35 over 37 plus negative 1 plus 1/3, 1 over 37. That's why we have the 0.027 by simplifying this given problem. So this means that the player can expect to lose about 2:7 cents per bet in the long run. So let's now discuss about Daniel Bernoulli, Poisson and Chebyshev. So in year 1738, Daniel Bernoulli was born in 1700 and died in 1782. He tackled the problem proposed by his older cousin and published his investigation in the Proceeding of the St. Petersburg Academy of Sciences. So as a result, the problem was subsequently become famous under the title of the St. Petersburg problem on the St. Petersburg paradox. So the question is, what sum should A pay B for the privilege of taking part in this game? For the game to be fair, A should agree to pay as an entrance fee the number of coins equal to A's mathematical expectation of gain. So let us therefore calculate this expectation. So the number of the outcomes in the night, because there is no logical limit for the number of the tails that might appear before the first head shows up. Thus, the expectation involves the sum of an in-night number of the terms as in night series. So, if there is a sequence of n, 1 tails before the first head appears, then B is to pay out 2 raised to 1 minus n minus 1 coins for these outcomes, and the probability that heads will show up for the first time on the ninth toss in 1/2 raised to n. So the total expectation of A is therefore given B2. So we have 1 times 1/2 plus 2 times 1/2 square plus 4 times 1/2 cube plus 2n raised to n minus 1 times 1/2 raised to m is equals to 1/2 plus 1/2 plus 1/2, and